Hi, welcome to another video on differential equations. We're going to be talking about inverse Laplace transformations. And like everything in the universe, it has an opposite or an inverse. Like happy, the opposite of happy is sad. The opposite of electron is a positron. It seems like everything has an opposite. So we're going to be talking about the inverse. So if we see here, if we, like we did last time, we took the Laplace of a function t, well, that just gave us basically a function of s, capital F of s. And so basically, a function of t is equal to the inverse Laplace of this capital F of s. So these are our functions that are the inverse. So the inverse Laplace of 1 over s is 1, and so forth, yeah. The one thing that we have to be careful about is these trigonometric functions. Okay, so if you have something like this, you'll definitely have to multiply it by k or k squared here, because that's what the original Laplace transformation is. And you'll see in problems what I mean by that once we start getting into it. And it's basically the same for most of these. Okay? So let's get into it. Okay, so we have number 6, and it tells us to find the given inverse Laplace transformation. Okay. So we have the inverse Laplace of this function. All right, so one thing to notice is that our function starts with an s. Right, we're starting off with an s. And then that means we'll end up with a function of t. So if we think back to our regular Laplace, we started with a t, and then we went to an s. And now we're going to be doing the inverse. So we're going to be starting with an s and going to a t. That's something to notice. If you completed it correctly, you'll end up with t's, right? Okay, perfect. So let's start off with this one. And like in the previous video, we said that if we had something like this, where it was quantity squared or cubed or whatever, we want to expand that, okay? So if we were to expand that, we get s squared plus 4s plus 4. And that's going to be all over the s cubed, okay? And what I'm going to do now is, since every one of these terms is over s cubed, I'm going to put all that over s cubed. And you can see why when you begin to realize that some of these s's will cancel out. All right. Well, so now you know that these s's will cancel, and it'll reduce to something we're more familiar with. And that's just that. Okay? Well, the inverse Laplace of 1 over s, that's simply going to be 1, plus the inverse of, well, we can see like this. 4 times 1 over s squared is the same thing. You could move this 4 out here and just work with the 1 over s squared, but it means the same thing. So the inverse of this is going to be 4t. All right. And if you're wondering why, well, this is our n factorial, and this is actually n plus 1. So it was a power of 2, so that means it was 1 plus 1. So that was, our n is 1. Okay? And so that's why we get t, because that was our n was 1, right? So we just have t. All right, so this is the same thing, but it's going to be a little different because this is our n factorial. However, this is a 2 factorial. Okay, so it was 2 times 2 times 1, which is 4, and that's why we have this 4. Okay? You can also think about it like, oh wait. So this is why it's smart to pull that 4 out. Okay? So because we don't have this, so this is supposed to be a 2 factorial, right? It's supposed to be. Because here, with this cubed, it is actually n plus 1, and our n in this case was 2, because 2 plus 1 is 3. Okay, so we should have a 2 factorial somewhere. And I did the factorial wrong. So we should have that 2. 2 factorial is 2 times 1, right? All right, so we should actually have that 2 somewhere in there. So what we're going to do is multiply that by 1/2 to make up for not having that 2. And so this means we're going to have 2t squared. Okay, so we have the inverse Laplace of the function is 1 plus 4t plus 2 times t squared. All right. So this, what we were doing here, just came from our basic functions, our basic inverse functions. So just as a reminder, it's supposed to be s n plus 1. Okay. So here we didn't have the n factorial, so we definitely had to make up for it by dividing by multiplying by this 1/2. Okay. And I think that's why it's smart to take out the constant, because then it'll confuse you like it did me right now. And I try to rationalize it by doing incorrect math, but that's okay. So this is how you do it. Okay, so we'll do the inverse Laplace of 1 over 5 times s minus 2. Okay, so, well, I don't really know I don't know, we don't have a transformation for this. So what I'm going to do is pull out a 5. All right, see if it makes it look nicer. So if I factor out a 5, I get s minus 2 over 5. All right. And well, now this is something I've seen before, because if I pull out that 1/5, which I can, I have the inverse Laplace of 1 over s minus 2 over 5. Well, I've seen this before because this is one of my inverse functions. Isn't it the 1 over s minus a? And if I inverse that, that's going to give me my e to the at, right? So in this case, my a is that 2 over 5. Okay, so now I have this 1/5 e to the 2/5 t. Great, and so that's the inverse of that function, the inverse Laplace of that function. Notice I went from having an s to a t. Great. Okay, so this is a much more, not complex, but it's a little challenging. Okay, so I have the inverse Laplace of this function, right? I need to find that. So what would you do? Well, I would definitely split it up to look like this. S over s squared plus 2 minus the inverse Laplace of 1 over s squared plus 2. And that's totally okay to do. Okay, so if we look at this one, well, according to our Laplace identities, this should be cosine radical 2t. Because if we go back to our basic Laplace functions, this was k squared. That 2 is in the place of the k squared, so what we did was make it the square root of 2, and if you were to square that, it would give us our 2. Okay? And for this one, well, that 2 is in place of the k squared, right? Right. And this one is going to be a sine function. However, for our Laplace functions, it was k s squared plus k squared. So if our k is a 2 squared, that means this has to be multiplied by a square root of 2 to the top and the bottom as well. So whatever you do to the top, you do to the bottom, right? So now I have the square root of 2, 1 over the square root of 2 times the sine square root of t. And that's especially what you have to be careful with, because these will definitely get you, because you definitely have to pay close attention, because there's going to be multiples of these, like these types where you have to like multiply by square root of 2 and divide by square root of 2 in one of these functions. So definitely be careful and understand what's going on here and how it becomes this. So we'll move on. Okay, so this is a problem that I'll show you, one of the methods that you'll need to be proficient in. All right, so can I split this up? Yeah, probably. However, I don't think that will do me any good. So what I'm thinking is, you know, I might try something. Well, if you are familiar with partial, fractions, then you're halfway to solving it. Because partial fractions is how you'll be able to solve this. So if I treat this as a partial fraction, I will have a over s plus b over s minus 4, because all I did was factor out an s there. Let's see, plus c over s plus 5 equal to s plus 1 over s minus 4 times s plus 5. All right, so if you know how to solve one of these partial fractions equations, all power to you. And if you don't, it's good to learn now, because you'll be using this a lot. All right? So if you don't know how to solve one of these, I think I'll take it step by step and try to hurry up so we don't go over like an hour video. So what I'm doing is basically multiplying by this denominator to everything. And this will cancel that out. And I'm left with this, s plus 1. And if I were to multiply this whole thing to this term, my s will cancel out. And I'll be left with a times s minus 4 times s plus 5. Great. And if I were to multiply this to this term, this will cancel out, and these two will cancel out, and I'm left with the s times s plus 5 times that b, okay? And if I were to multiply this whole thing times this term, these s plus 5s will cancel out, and I'm left with c times s minus 4. Great. So now I have a times s minus 4, s plus 5, plus b times s plus 5, plus c equal to s plus 1. All right. Boom. We're pretty close to solving it. Okay, so how do we solve this? Well, usually what I do, and it's one of the fastest ways, is make s equal to a number that will make like one of these whole terms equal 0. So for instance, if I set s equal to 0, that would be a times negative 4 times 5. I'm just putting 0 into all the s's, plus b times 0. Oh, great. Anything times 0 is 0, so that's a 0. And that's also a 0, right? That'll go to 0. And this will simply be a 1, because 1 plus 0 is 1. And so now I have negative 20a equal to 1. Well, if I divide by negative 20 to both sides, great. I get a is equal to negative 1 over 20. So I solved one of my variables already. A is equal to negative 1 over 20. And for time, b is equal to 5 over 36. And c is equal to negative 4 over 45. I just did that all in my head right now. Great. So we're going to replace these variables there into those a, b, and c. And then we get, let's see, I'll probably do it over here. Hopefully you got that. Partial fractions, definitely got to know it. So I can say this is negative 20 times the Laplace of 1 over s plus 5 over 36 inverse Laplace of 1s minus 4 minus 4 over 45 times the inverse Laplace of 1 over s plus 4. Okay, well now this is a lot easier. We can see the inverse Laplace of 1 over s. That's going to be 1. Great. Inverse Laplace of s 1 over s minus 4. That's 536 times e to the 4t minus 4 over 45. The inverse Laplace of 1 over s plus 4, well, that's going to be e to the negative 4t. Was it a 4? No, it was a 5. Excuse me. So e to the negative 5t. All right? And that's how we find the inverse of that. And that is basically the inverse Laplace transformation of a differential equation. Thanks.